Hello, you're listening to Wendell Boucher, the author of these audio-visual course presentations focusing on modern switch mode power supply design. This is not one of the courses, it's simply the introduction, and it consists of 4 parts. Part 1, we discuss the prime motivation for creating these courses in the first place. Part 2, we briefly review the history of modeling techniques, including state space averaging by Dr. Middlebrook and Dr. Chuk, small signal and average model limitations, and then we will introduce a unique modeling tool without the limitations. The most interesting part, however, runs for about 60 minutes, and we will run multiple demonstrations of power supply performance using schematic entry. The objective of these demonstrations is to demonstrate every behavior that affects phase and gain. Topologies will include voltage mode, current mode, and resonant mode. And finally, there will be a closing summary of services offered. Why are these courses offered now? The playing field is no longer as level as it was 20 years ago, mostly due to the global economy. Non-recurring engineering dollars have all but disappeared. Time to market is at an all-time minimum. But in spite of these pressures, product quality must still be preserved. Perhaps it's time to take a fresh look at how we can compete more profitably. What must we do to compete profitably? There are several ways. Reduce electrical circuit design time by a factor of at least 3 to 1. It's quite possible to do that. Reduce design risk to 0 for all practical purposes, and we can show how that's done. Use laboratory time and personnel more effectively. Employ modern computer-aided tools more effectively. In short, we must automate engineering, just as production has traditionally automated assembly. How does this approach differ from previous methods? Actually, it's an extension of existing practices by successful companies, and the author's work for several of them. However, it employs unique software that goes beyond average modeling that the author has been using since 2004. This is very important. State space modeling techniques are no longer required to close loops. A knowledge of heavy mathematics is not required to use this approach. Also very important, the major design vehicle is a computer, not a breadboard or prototype. It is very flexible and not tied to any specific components or topologies. This means it can be used way into the future, will not become obsolete. We cannot emphasize enough that the modeling approach must be accurate. The model itself must truly represent the circuit being designed. And because of that, component characteristics must be either known or measured. We're now going to give you a very, very brief review of modeling techniques to bring us up to date. It started about 1976 when Drs. Middlebrook and Chuk collaborated to bring us a new technique called state space averaging. They wrote an IEEE paper entitled A General Unified Approach to Modeling Switching Converter Power Stages. It's very thorough, and in that paper they defined for the first time in history 3 categories of power supply, switch mode power supplies that is. One being the buck, the other being the boost, and the third being the flyback. Now there are actually only 2 families, the buck and the boost, and they are duals of one another. The flyback is the combination of the buck and the boost, and in fact is called a buck boost. This is what's important. The models are required to calculate gain and phase accurately. In order to do this, the switches had to be removed from the models. That made them run very quickly compared to the time it would take to run them with the switches in there. The usual ratio is 1,000 to 1 or better. As time went on, many researchers built upon the original work, and still do, and I was one of them. These days, most of the models are large signal average models. But here's the point. However, all of these models have limitations that the user has to be aware of. All of the model creators did warn us of these limitations. They knew what they were and let us know. The limitations are due to the missing switching currents and voltages. And clearly the reason for that is because the switches had been removed, as we show right here. So the bottom line, and this is very important to understand and remember, only real hardware or a switching model will yield accurate measurements of gain and phase. And I'll say it again because it's very important. Only real hardware or a switching model will yield accurate measurements of gain and phase. We're about to show a model that will actually do that. Now here we introduce a unique modeling tool without the limitations we just spoke of. And here are some of the important features of this software tool. Your model includes switches just like the real hardware does, and that's the main reason why we don't have limitations. Steady state operation is reached in seconds regardless of component values. For example, if we have a switch mode power supply, it's a current mode buck regulator, let's say, with one output, the steady state operation is reached in roughly 6 seconds. And it doesn't make any difference whether you have 1 microfarad for an output capacitor, load capacitor, or whether you have 1 farad. Clean phase and gain curves are produced with no switch noise in the plot. The plots are very easy to read and understand, make calculations from, and so forth. They too are calculated in seconds regardless of frequency range requested. For example, if we're running at 100 kilohertz, we might like to see a plot between 10 hertz and say 80 kilohertz. So we can look at the half frequency phenomenon if we want to, called half frequency oscillation sometimes. It'll do that in roughly 6 seconds from 10 hertz to 80 kilohertz. If we take the start frequency from 10 hertz down to 1 microhertz, it will still do it in 6 seconds. The phase and gain are calculated with an accuracy of 0.5 dB and 1 degree, and that's a guarantee from the manufacturer, the creators of the software product itself, because of the way they do the calculations. An unlimited capability to model any topology, even those not yet conceived, is very important to us because it eliminates obsolescence. Overall accuracy is dependent on the accuracy of the model and components. This is very important to understand. Components are measured in a lab or their published values are used. A breadboard, if any, is used only as a proof of design breadboard. What we mean by that is we build a breadboard, we measure the results, look at the data, compare that data with the calculated data from these models. And they should agree very, very closely, usually within the component tolerances themselves. A proof of design breadboard test time is typically 2 days maximum, and that's for a complicated circuit. The one I just spoke of is a fairly simple circuit. Typically takes a half a day to do this test. Half a day to, say, a day. Now before we start, please accept my apology for any vocal typos. There are two that I know of, but you senior engineers will recognize them, I'm sure, and make the appropriate corrections. The presentation was delivered ad-lib with no script during the demonstration phase, and no correction was possible, hence the typos. Please note that you can hit the print screen button on your keyboard, next copy to the paint.exe program on your system, then print it. Pause the presentation anywhere you wish to, or simply note the elapsed time seen on the lower right of the Windows Media Viewer and do it later. So having said that, let's get on with the demonstrations themselves. I'm sure you will enjoy them thoroughly. We will begin by showing you two models. This one is a low-pass filter. We're going to modulate it with an AC signal in the same way we'd do it with an AC analysis using PSpice, for those of you familiar with PSpice. In fact, we're using symmetrics to do this one. We're going to modulate at this point, go through the filter, look at phase and gain at this node. Then we're going to do the same test with the same filter. We're going to modulate it at this point. We're going to generate a pulse by comparing a sawtooth to the control voltage, which is being modulated. Generate a pulse at this point. Generate a square wave at this point, which is a modulated square wave, and look at phase and gain at this node. And if the phase and gain at that node compare with the phase and gain at this node, we've proven our point. Now, the claim of Simplis is that we can measure with an accuracy of 0.5 dB at 1 degree. You'll see it's far better than that. And we'll begin now. We're finished with the analysis on this one. Here's dB. And we're going to look at phase. We have two scales here. We can put them on the same scale, but it's better if we don't at this point. This is the gain in dB through the filter. This is the phase through the filter. Now we're going to minimize that. Go to the switched model, but with the same filter. And we're going to run that. Note the time, 5 seconds, we're done. We're going to measure dB. There it is. Minimize that. Measure phase. And now you're looking at two gain curves at this point, two phase curves at this point. Now we're going to expand. It's very easy to do it this way. We'll try to expand the gain curve first. Sooner or later we should see two curves. There. That was a little difficult, so let's try it again. They're so close, it's almost impossible to separate them, but you can see it. Again. There. Now you can see two curves. See them? That's how close they are. They're practically on top of one another. Now let's look at the phase curves. A little easier to see. Phase is a more sensitive parameter, of course. And there are the two phase curves. Now, reiterating, there's a curve underneath this blue line. It's a red one right here. And it's so close to the blue line, which is done using Simplis through switching noise. This one's not through switching noise. This one is. And we're going to remove these to show you the original curves by doing it this way. Hide selected curves. There's the original curves from the AC analysis. And we'll stop at this point. I believe we proved sufficiently that you can calculate gain and phase through switching noise. But now we're going to give you some more examples. This example is a flyback. We're going to show you the right half plane 0. And the circuit values come from this Unitrode presentation. And briefly we'll talk you through the circuit. The purpose of this portion is to generate a pulse. The V control node is right here. And when we vary that voltage, we vary the pulse width, of course, up here. We're driving a switch, transform with a primary and a secondary. Right now it's a 1-to-1 ratio. Forward diode and load capacitor with ESR, load resistor. Feedback comes down this path through this way. And this is a type 3 compensation amplifier with 2 independent poles and zeros that we can adjust. And the way we adjust those is to bring up the so-called F11 window. Expand that a little bit. If you take a look here, this is called the F11 window that we just opened up, and you'll see that the components associated with the compensation amplifier are done with equations. And what we do is to control the zeros by simply typing the number in here. There's a 0 at 104 Hertz, another one at 104 Hertz, a pole at 1500 Hertz, another pole at 10 kilohertz. SV is the gain of the compensation amplifier, and Rin, of course, is the resistor over here. You can't see it very well because we shrunk it down so much. We'll blow it up a bit for you now. And we'll close that down a little bit. Now you can see the values. You notice we put an A after these numbers, but we use the same designations that Dean Venable would use. This is usually R1. Rin's a good name for it too. This is usually R2, C1, C2, R3, C3. The reason we put the A on them is so we can find them when we do this. Closing loops is basically, it's not quite this simple, but it's basically placing compensation zeros on poles and poles on zeros. That's how they cancel. We look at the values by looking at our Simplis edit netlist after processing, and we haven't processed it yet. That's the problem. Alright, close that down. And we're going to put a probe at this point. Shrink this down so we can see it better. Close that F11 window. And we're running a phase and gain analysis. We do this in order to put both curves on the same y-axis. That's not a very good looking curve, and I'm going to explain to you why in a moment. F11 window again. Have to click there to do it. And Close it. That's not where the number is. Alright, at this point you see we have capacitance with 1 micro series with it. We did that to show the right half plane 0, which we'll show you in a moment, but let's change that back to 0.01 ohms and run it again. Now that's a better curve, but you'll notice where we're crossing over. It's only about 700 or so hertz. The reason for that's because of the right half plane, which introduces considerable phase shift. Now we're actually going to show that to you. Close this down. We have to do this on purpose. We've got to bring that back to 1 micro. By the way, see how easily we change that part value. Bring the circuit back down for you. I'm going to remove this probe. Run it again. Notice the time. 2 seconds, 3 seconds, 5 seconds, we're finished. And we're in a switching mode. dB relative voltage, V out over V in. Now clearly we have a pole here, and somewhere in here there must be a 0, but it's not the ESR. We've taken that out. Now we're going to minimize that and go to another circuit. In this circuit we have calculated, using this equation and the load value that we have, a frequency of 3600 Hertz. So we've simulated that power stage just for the purpose of this analysis, this again to prove to you that we can calculate it accurately. We put a complex pole pair in here, and we put a right half plane 0 in here with a negative resistor, with this thing having the dimensions of 3600 Hertz. Now we're going to run this circuit and probe dB voltage at that node. Now you see two curves. The red one was the one we did on the actual circuit, which has a right half plane 0, and the second curve, the green one, is the calculation we made by actually setting up a right half plane 0 and a pole pair at this point, and right half plane 0 about in here. See how close they are? Now, there's how close they match. The difference between those two curves is roughly pick a spot anywhere, bring this one over. Roughly 0.2 dB, well within the 0.5 dB they talk about. And not only that, some of that was the operator's intervention too, because we had to set this up empirically. Alright. Now I believe we've shown you the right half plane 0. What you're looking at now, of course, is a canonical buck, but in average current mode. And the element values, except for the compensation amplifier, we've optimized that a little more, come from this unitrode presentation. And again, this section of the circuit is to generate a pulse to the switch. Reverse diode, buck inductor. We're sensing the current here with a parameter called RI. And this is the load capacitor with its ESR. This is the load resistor. And coming back down, we sense the voltage at this point, compare it against a reference. This compensation amplifier, this is actually a type 2 amplifier. We then mix that with the feedback coming back from RI at this junction. It's the way it's always done. And go through another operational amplifier. It's called average mode because we're using a compensation amplifier. Mix that at this point. Now we're going to run it just to show you the voltage feedback path, gain and phase, to show you we've done it already. We'll run it. Again, look at the time, 4 seconds, 6 seconds. And there's the power stage, so-called. Excuse me, not the power stage, this is the voltage feedback loop. And we're going to put both of these on the same axes, and there's how it looks. We crossed over at 10 kilohertz. This is almost picture perfect because we put poles on zeros and zeros on poles again. And if you look down at this corner here, you'll see some numbers for the X and Y. As long as this pointer is on the curve, on the graph itself, wherever it is, you'll see those numbers. And ignore whether they say dB or hertz or phase or whatever it says down here, because that's simply the label that's over here. By default, it picks up the last label. So we're looking at the crossover at this point, and our phase is roughly 66 degrees, which is quite healthy. The gain margin, when the phase crosses 0, is roughly 15 dB. That's good too. So we're going to close that down. We're going to remove this. And we'll look at a couple of more things. dB relative voltage, out to in. This is what it looks like if we don't have current mode control. This is the gain of the power stage without current mode. We'll save that. Probe dB relative voltage, out. This is the control point. Current mode gives this to us. Now you'll see something interesting happening here. We've got a 0 at this point, that's ESR 0, and we have a pole over here. Now, in order to show you the half frequency phenomena, we're going to take out the 0 at this point, which is the ESR of the capacitor. It's noted right here. Blow that up for you so you can see it. There it is. It's a parameter called ESR. We're going to go back to the F11 window and find it. It's right here. The design value for that ESR is 0.015 ohms. We're going to make it 1 micro, just so we can eliminate that ESR. Close the window. Run again. Please note how quickly this runs. And now we're going to look at dB relative voltage, out, over V control. Now this is the classic current feedback curve that you'll see for gain. There's a pole here, there'll be another pole down here. This pole is when the current loop runs out of gas. Has no gain for practical purposes beyond this point. Now we don't see any right half frequency phenomena. The switching frequency, by the way, is 100 kilohertz. So we'll keep that there for the moment. And you see this parameter Ri, that means the number of volts you get here for the number of amperes you see it going through the coil. Right now it's set to 0.05. What we're going to do, however, is jack that up to 0.3. A lot more current feedback from the coil. Going to run it again. Probe dB relative voltage, out from V control. And now, this is the curve we had originally with Ra equal to 0.05 and Ri is now equal to 0.3. The gain came down. That is, the DC gain came down. But look at this. This is the half frequency phenomena right here. It's right at 50 kilohertz, where it's supposed to be. Now we're going to close that down and do two things now. Probe dB relative voltage out over in, and there it is more clearly if you want. Now we're going to look at the phase. Probe phase relative voltage out over in. This is what it's supposed to do. We'll put those on the same scale, and you can see the gain coming down, and the gain starts to shoot up at the same time the phase goes down. It can be very dangerous. One last point is to show you what the loop looks like again with that too much feedback, if you will, where we have too much feedback. Place the Boucher probe here. Simulate a run. And that's what the voltage loop would look like. Are we in trouble? No, not really. I'm going to raise the ESR though in a moment. Remember, the ESR is 1 micro right now. So at this point we actually have 65 dB. That's not bad. We're fine here because this never comes up to 0 at this, with these values. And we'll shut that down. Put the ESR back in again. We have shown you the half frequency phenomena. Run. This is what it looks like with the original design figures in there, but with too much feedback coming from the coil. Now we're still not in trouble, but you could clearly see if this were to come up to this point, we would be in trouble. I believe we've clearly demonstrated the half frequency phenomena. We'll go on to some more tests. We started to show you earlier where you get the element values for these components, but we hadn't run the analysis yet, so we won't have them. In this case, however, we have run an analysis. We wanted to know what the values of these components are as a result of placing these poles in zeros. You simply go up here to Simplis, edit netlist after pre-processing, and we look for capacitors with an A after them, C1A and C2A. Remember, that's how we label them. And here's the value. That means in real practice, we'll pick a value close to 8926 picofarads. That's what it really is in this model. Now that can be varied, 10 or 20%, won't affect things that much. Now we're going to show you some more AC measurements. This is a switching model, remember. This is a good test to make. If you haven't calculated, it's a good one to make anyway. dB relative voltage out, in. This is what the compensation amplifier is actually doing. There's a pole way back here, and we'll show it to you in a moment. There's a 0 at this point, another pole at this point. Now that's the amplifier itself. That gain measured from this point to this point with the compensation networks. It's also important to do this. Output of the amplifier to the input of the amplifier. Now we're looking at the open loop gain of the amplifier, and it's always necessary for this compensated curve to be well within this one, certainly within 5 dB. If it doesn't, what happens is the pole emerges. That's how we generally describe it. And if we say we had a -1 slope, it'll turn into a -2 if the internal pole emerges. I'll show you that whole amplifier curve. We'll shut this down. Simulator, choose analysis. This one will rather amaze you. I'm going to take this down to millihertz. I'm going to run it again. Not sure he went down enough, but we'll see. No, it still only takes 7 seconds. No, we didn't go down far enough. Close that down. And take it down to a microhertz. Nothing on the market can do this except this software. We're down at 1 microhertz, and we'll do both curves this way, put them together. This is the amplifier, open loop gain. Oh, excuse me, it isn't. This is the loop response. Let me close that down. dB relative voltage out over in. This is the compensation amplifier gain. Minimize it. Out over in. This is the open loop amplifier gain. This is the open loop amplifier gain. Its internal pole is at 4 Hertz. It's right here. In fact, if we ask for that, right here, 4 Hertz. That's what it's designed to be, as a matter of fact. It's like an LM107. Now this curve must stay within this curve in the active region, which is down here. And you can see that this is the open loop amplifier gain. It's 110 dB, and if we do that, we can see it. 110 dB right here. And this is a minus 1 slope. And again, we say if this curve ever comes close to this one within 5 dB or closer, then this one will control this curve. And we don't want to do that, of course. Now, before we forget it, let's change the analysis back to an AC at 10 Hertz again. You notice it didn't take any longer to run that than it does when we're running it now. Makes no difference at all. And there we are. Now to remove this, we go back and set this up with a proper value, which is 0.05 by design, and run it again. And that's how we designed it. Now in this next test, what we've done is to raise the load to infinity for all practical purposes. We're going to pulse it. I should say replace it with a pulse. It pulses from 0.5 ampere to 20 amperes at 100 Hertz. And what we do is set it up to give us a pop analysis followed by the transient analysis. That's how you do it. And by pop, I'll explain that again. Pop analysis is an analysis in which everything reaches steady state. So in this case, we're asking it to reach steady state, all voltages and currents. And when it reaches that point, then pulse the load. And now we're going to run it. Notice the time again. 2 seconds. When this reaches 100, we're finished. About 8 or 9 seconds. And we can look at the load voltage, and there it is, and we're pulsing. Now if we want to know what the value is, there's several ways we can do it. We can bring the cursors down and measure it, but the easiest way is to do this. Measure transient, peak to peak, full, click. There's our number. It's about 512 millivolts, 513 to be rounded. 513 millivolts peak to peak, this point to this point. Not bad. We can also look at other voltages. To look at voltage, we do a right click left click, we get a pointer. This is what the op amp is doing while this is happening. Certainly not overranging, as you can see. We're going from roughly 0 volts to about 1 volt or so. And we can look at the output of this op amp. Same thing, we're going to roughly 6.2 volts. And we can look at the pulse and see what it's actually doing at this point. And perhaps we should bring another grid over here and look at the current so that we can look at some important place like this. You see what's happening? The pulse actually goes away. It disappears at that point. Now we can walk along that curve. Let me do this first. Make that larger. We can walk along the curve by using the left and right arrows. May take too long to get there, but there we are. There's the other one. You can see what the pulse width is doing. It changes in this region. Trying to recover, of course. Now we can look at some other waveforms while we're at it. This is the sawtooth. And this is the control voltage. We'll shut down for a moment and do another test for you. Before shutting down though, let's change the circuit, show you how quickly you can do that. Open that line, connect the generator to a load because it's a current generator. It's not connected to anything else, but that's okay. This value up here is a parameter. Open up the F11 window, change that load back to 0.334. Now we go to this generator, expand this a little bit so you can see what we're doing. Close the window. Take this generator, that's a left click, right click, edit part. Make it 0 because we don't want more than one generator running at a time. Go back up to the input. We're going to make this generator 1. I was going to look at line susceptibility at this point. I believe we're ready to go. Choose analysis. We don't want transient. We want AC, pop. And there's our AC, we run. That didn't take more than about 30 seconds to do. Now this one you see is 0 because we turned this generator off and we left this in, so we can take that out with a click delete key. And we can look at the output. dB voltage at this point. And this is the attenuation that we have from the line, which is very good. Real life would probably be a little bit higher. We optimized it here, of course. But you can see that compared to a voltage mode would put us up in here somewhere. Slope would be about like this. We're down here with current mode. This is one of the benefits we get from current mode, of course. You all know that. Not only takes the coil out of the picture, but gives us good line susceptibility to boot. Now we'll go on to another test. Now we brought up a model of a canonical buck again, but with voltage mode feedback. We're going to demonstrate several phenomena with this one. We have a line filter over here, and it's in place at the moment. We're going to demonstrate what the line filter does to your loop response in terms of looking at the impedance of the power supply versus the impedance of the filter going in this direction, going from right to left. Again, this section generates a pulse, goes to the switch. The dB voltage is coming, the line voltage is coming from here. The buck conductor, reverse diode, cap with ESR, and a load. And we're coming back with a type 3 network again, because we have a complex pole pair. In this case, we have to compensate. So let's run that without ado. Going to do an AC analysis, same range we've been using. And there it is. We'll put them on the same axes. Now, we're crossing over basically at about 7 up to 10, somewhere in this point. We put this dimple here on purpose. And we'll tell you how we did that in just a moment. You can see a dimple in the gain curve. You can see a dimple in the phase curve, which is much more emphasized, of course, because phase is so sensitive. Yet we have a good crossover. There will be no oscillations at this point. Now, the reason we got the dimple is because the impedance of the filter versus the impedance of the power supply. Now we're going to take that damping resistor out of the picture. That's 50 ohms. Now to see the overall picture, perhaps I can expand it and show you a little bit more here. A little hard to see, but it's 50 ohms. There you go. Now we've taken the damping away, and we're going to run the same plot again, which is phase and gain of the loop. Now, if you take a good look at it, you'll see we have a problem here. The gain is 1, the phase is also at 0. It's always necessary for the gain to be at 1 when the phase crosses, for it to be a problem of oscillation, of course. But it's happening, as you can see, right there. Now, we're going to predict an oscillation, and we're now going to show it to you. We're going to take this same circuit, reduce it down a little bit for you, so you can see most of it. Our load is over there. All right. Choose analysis. We're going to do a transient analysis from 0 to 40 milliseconds. Now, when these numbers reach 100, we're finished. We're almost there. Look at the load voltage. Pay no attention to this. We have not optimized anything for the turn on yet. If you take a look over here, you'll see something interesting happening. Now, what we're going to do is bring down the cursors for a purpose. We want the cursors to give us a window to look at, which is this window right here. Now we're going to say measure, more functions, measure, transient, frequency, cursor span. We're not doing a pop-in analysis, we're doing a transient analysis, so we have to use cursor span. Say OK, and guess what? Look up here. We have an oscillation of 699, roughly 7 kilohertz. You might jot that number down. It's 7 kilohertz. Now let's go look at some impedances. We'll run that again with this down before we look at the impedances. We'll make one more run. We've now dampened the input filter. Look at the output again. Man, it's clean as a whistle. All we got is normal ripple on it. Now let's examine more closely what's going on up here in the input filter. We'll take this out, make this number, and to left click, right click, left click, change it to 0. And we have two generators. We're going to make this one equal to 1 also. Done that. We're going to open up the circuit, connect this generator and its 48 volt battery to the power supply, and we're going to connect this generator . that power supply. I'm going to change this voltage to, we don't have to do this, but we'll change it to 0 because we don't need it anymore. Otherwise, it's going to pull up massive current through this path, although it will handle it okay. And we're going to say simulator run again. We're done. Probe. More probe functions. Impedance. Okay. I didn't see the probe. Let's see. The reason we didn't see the probe is because we were running a transient analysis. We have to run an AC analysis for this test, so we'll run it now. Probe. More probe functions. Impedance. Now we have a probe. We have to put it right on the generator itself. And now we're looking at the impedance of the power supply. This is the magnitude of the impedance. It's actually negative, particularly back here. And but we just need to know the magnitude. Now we'll save that. Probe. More probe functions. Impedance. Okay. Look at this point. And we're looking at the magnitude of the filter impedance, looking into the filter from the power supply side. Now the rule is this curve should never exceed this curve. That's the rule. If it's down below, even down here, we can see some effect from it. We're going to show you that in just a moment. So let's save this. This is when we had a problem. In fact, we'll expand that just to go show you. Well, guess what? There's 7 kilohertz. So when it hit this point, we had a problem right in here. Right? And we predicted it, and we measured it. Let's save that. Dampen the filter at this point. Run it again. Each time you make a change, you have to rerun, but it only takes seconds, as you can see up here. Probe. More probe functions. Impedance probe. And we're looking at the filter again. Now, you see 2 curves over here. They're about the same everywhere until we get to this point. When we had the 20 ohm resistor in, when it's in place, we see the blue curve. When it's not in place, we see the green curve, and we will not oscillate here, but even though we're this far away from that impedance, and we can in fact measure that difference if you want. And we can, yeah, but we'll measure it. I think we're on the blue curve. Let's see. Yes, we are. For that one. This will be on the red curve. And the difference is roughly 71 ohms. There's a difference of 71 ohms between those 2 curves, and yet we can still see the effect of the blue one. All right. Now we're going to shut down for a moment. Now what we've done is to take the filter away and power the power supply with a 48 volt battery so that we can look at the loop phase and gain again. And we're going to run it and show that to you. Now if you take a good look at this, we're crossing at 10 kilohertz. Good phase margin, about 71 degrees. And a good gain margin down here, but you see no dimple whatsoever. There's nothing around 7 kilohertz. Again, to show you that the impedance of that filter can cause problems. So I believe we demonstrated the impedance mismatching problem to you. You can see how easy that was to do. Now we're going to show you with that same circuit that we can go from discontinuous to continuous and back and forth automatically. You don't have to do anything special. Same circuit, just going to change the load resistor. So we'll run the AC analysis again. Probe dB relative voltage out, in. This is what it looks like with 5 ohms. We're going to take this up to 50 ohms. Run it again. Probe dB relative voltage out over in, and all you can see that really happened was that the Q went up because we're at higher value of load resistor now, but basically curve looks about the same. I'm going to save that. We're at 50 ohms. We're just going to take it up to 60 ohms. The point at which we go from one mode to the other, that is discontinuous to continuous, is between 50 and 60 ohms. Run it again. It's easy enough to calculate, but I won't waste the time doing it now. Probe dB relative voltage out, in. Now look at the curve. It's a -1 slope. This is a -2 slope. Now we can look at the phase also. In fact, we'll do that with this one. Phase relative voltage out to in. And that phase curve is this one right here. And if we click on all of these, this is the curve with a load resistor of 5 to 50 ohms, load resistor of 60 ohms, and the load phase at 60 ohms for the power stage now. It's all power stage measurement. You can see we're well above 100. It goes to 90 and it takes off down here, and it normally does that. It's only going to hold for a while. It's not a non-minimum phase network. Now, while we're doing this, change the analysis to a pop analysis. By the way, I can show you something else. We just did this one, so we'll cancel out. If we want to look at waveforms, actual waveforms, we do a right click. We do a right click and a left click there, look at it. The waveform we're looking at is the AC waveform. Something to keep in mind. You can be tricked by it sometimes. But if you want to see the actual switching waveform, just say pop, pop voltage, pop differential, or pop current. That's all we can get when you're doing an AC analysis, but we can look at them. For example, there's a sawtooth. Pop voltage, and here's the control voltage, right at this point. Now, let's show you how to do that a little easier. Go into pop. Now we say run. It just does the first part, which is the pop analysis. Now right click and a left click gives you a probe that will measure voltages and currents anywhere you want to measure. For example, we can also measure probe power and device, measure the power of anything. Want an average of it, click up here and you got the average. That's supposed to be 5 ohms. We'll put it back to 5 ohms and then run it again. Probe power and device. It's a bit higher now, it's 31 watts. Now we want to do one more experiment. What you're looking at is a 2 kilowatt, 2000 volt LCC high voltage power supply. We're showing you this so that you'll understand it, that we can also look at phase and gain with systems that control power, I should say, by varying frequency. It's done in this way. We have a square wave at this point driving the LCC components. Square wave comes from a bridge normally, but we're simplifying the circuit so we can do this in a demo mode for you. That's the L. That's a C. The other C is a reflected C in the transformer. It's a step-up transformer, 1 to 8 to 8. This is the load capacitor and load resistor. We come back here and we sense the voltage and we measure it. This is a compensation amplifier, type 2. Come back through here. We modulate at this point. We convert this DC modulation to a frequency modulation by simulating this 1806 chip. I'll expand this now for you. By the way, the author always draws circuits in this manner. It's a very good way to do it for board layout. And that's one of our subjects, by the way, in our courses, is board layout, so that you don't have a hidden circuit problem. Power goes from left to right. Feedback goes from right to left. The author always draws circuits in this manner. When you do, you'll have very few crossovers. Anyway, let's get back to the simulation. This is an AC analysis using Simplis. You can see it's a nice curve, very straight line, very well behaved. Crossing over about, as I recall, about 10 kilohertz. 10 kilohertz. Angle about 83 degrees phase. And the gain margins in the order of 13 dB, which is quite healthy. Now we're going to show you, expand this a little bit for you. And we can measure some voltages by going into the pop mode. And running in the pop mode. This is the output voltage. It's regulated so the average is 2 kV. That's what we want. Power. In this case, is 2 kilowatts. There we are, 2 kilowatts. We can look at the current in the inductor. Measure the RMS value if we wish. We can look at the voltage on the primary. It looks like that. That's very typical. Another interesting property is we can look at the LCC, of course, is voltage differential. We can look at the diode from here to here. Diode voltage, close that down, and we'll measure the current to that diode. This is a property of LCCs. The current to the diode has ceased before this voltage actually reverses. So we don't have to have diodes with very, very fast recovery. Show it to you in a little more detail. The voltage is still up there. Diode current has ceased. So we've got a lot of nanoseconds to recover in. This comes down very slowly. It's not like hard switching at all. Interesting property. Now we can also do this with any of these circuits. We can say add curve, and we can say TEG. We're going to do an integral. And what do we want? We want this voltage times 1E8 divided by 1 centimeter divided by 100 turns. This is how the author always does it. Notice we're going to look at the integral of voltages across this, which is our flux density, if you will, in Gauss. And we get it by multiplying that voltage across the primary by 1e8 divided by the number of centimeters. In this case we make it 1, and the number of turns we make it 100. Say OK, and there it is. And now we can bring the cursors down and measure that. It's about the easiest way to do it. Go from that peak, go from the lowest value, and in this case you see 1022K, that's kilogauss. The actual number of Gauss is half of that for the core loss. So we would look up the core loss for 1 centimeter and 100 turns. We were to use that. It would be 500 Gauss we would look up. We can do the same thing with any inductor value. Now this is to show you we can actually change the frequency. And in fact, this is what it does. And this is calculated using state variable programs written by the author, especially for doing LCCs. You can do it in seconds to come up with all these values up here. Matter of seconds, and that's for sale also, by the way. And I think we'll stop at this point. We're running out of time for this particular presentation, so this is the last circuit we'll show you. This is a canonical buck with P current mode. We mix the two signals, the current feedback at this node and the sawtooth at this node. Mix that with the control voltage, and this is peak current mode. What we're going to show you is line susceptibility and how it peaks up. At first we're going to show you the loop as it's closed. We'll run that very quickly for you. And you can see by placing poles on zeros and zeros on poles, we have a nice looking cross over here. Almost picture perfect again. I'm going to shut that down for a moment. Make a couple of changes here. Make this voltage 1. We'll look at line susceptibility. We take that out. Make this voltage equal to 0. In simulator, run again. And we're going to look at the output signal. It's not what we wanted, so we'll go back and see what we have to do to change that. There was nothing to change. We were just looking at voltage instead of dB. But now what we want to show you is we're going to step the gain coming through the current path, if you will, over this range of 0.765 to 77 to 775. We can do that with set up multi-step. There's RI, the parameter. There's our list. We can change it at will. And we're going to run it now. This pass number 1 was 765. You can see the number up here. Pass number 2 was 77. Pass number 3, 775. Even with 3 passes, we've only taken 20 seconds. 20 seconds. Now we can say probe dB voltage and look at the output. Now, the red curve was the first value, and a 3% change gave us the green curve, and another 3% change going in the same direction gave us the blue curve. So the optimum point is right here. Whoops, back where we were. Optimum one is this. It means in real life you're probably going to move more than 3%. The duty cycle is going to change. Lots of things are going to change on you. So you'll be probably operating in this area in the real world. But at least you can measure it and look at it and do deviations. We can do Monte Carlos, lots of things, but no time to show it to you. Now, let's look at the waveforms which control that line susceptibility. We'll do another analysis, a pop, so we can look at the waveform quicker. Run it. We're finished. Right click, left click, probe. Here's the sawtooth. And here's the voltage that mixes with it. For the highest line susceptibility, you want the slope of the sawtooth to be 1/2 the slope of the current voltage coming back. There's a voltage proportional to the current when we mix them. This one wants to be 1/2 the slope of this waveform. It's as simple as that. They're actually there at this point. We can measure that if we want to. We won't take the time. Now, wrapping this up, I think we have shown all of this phenomena with demonstrations applied to actual power supply designs.